Hey everyone, welcome. In our company, we had the problem for a long time that before people were able to work with data, they first had to set up their own infrastructure. And that was cumbersome, and we finally came to the decision that we want to centralize this whole part and actually build what we call centralized processing platform, where one team is managing the infrastructure for a lot of other teams. And that's why we're here today and actually talking about continuous applications at the scale of 100 teams with Databricks Delta and structured streaming. So what can you expect from us today? We will talk a bit about technical details of our general setup, and as well as some of the use cases we are running on that infrastructure, as well as some, I would say, more higher level, like organizational things, how the general setup is on our side. So first up, we will be starting with a short introduction of where we actually come from, of Zalando. Then we will have the overview and like the technical details and organizational details of the processing platform that we are building. Then I will hand it over to my colleague Slava to talk about the Databricks use cases we are having, and then we will wrap it up with the lessons learned and the recommendations that we can give you should you face similar issues. So who are we? Both Slava and I, we are data engineers working for Zalando. We've been on the topics for quite some time already, and since about a year, we are working together in the data lake team in Zalando, and also started working together on this processing platform that we are about to talk now. And just before I tell you a couple things about Zalando, just hands up, who of you knows Zalando? Okay, that's not that many, but it's actually pretty much what I expected. Zalando is a European company that was just founded as a startup around 10 years ago to sell shoes online. By now, we actually grew to a size of, well, we actually became the biggest online fashion retailer all over Europe. So that was like a quite steep journey, and right now we are also at around 5.4 billion euros in revenue for the last year. So growing that fast also meant we actually grew to a size of around 15,000 employees in the company already, of which 2,000 are working in tech alone. And that's exactly where our playground starts, because 2,000 people working in tech means that there's like 150 or to 200 teams who are actually eventually one way or the other going to work with data. And this is exactly where we centralize that whole thing. We are running a central data lake, and this is the first thing that I want to now talk about a bit. When we're talking about a data lake, we're usually talking about three big areas, which are ingestion, storage, and the serving layer. And what does that mean for us? Two most important ingestion pipelines that we are operating is once we are having a data warehouse that is still running in the data center, but there's still like a lot of valuable information that can be extracted from there, and that needs to be present in the data lake as well to be able to provide that to our users. So we have a data pipeline that gets the data from the data warehouse, which is one of the pipelines that we'll be talking about later as well. And the other big pipeline I want to mention is one that interacts with our company-wide event bus, which is a wrapper around Kafka, which is called Nakadi. It's an open source project. You can check that out as well. And this is the second pipeline, which is one of the Databricks use cases that we want to showcase later on as well. Storage for us is pretty simple because most of the company is running on AWS, so all our data actually gets stored in S3. This comes not only with the storage of the data, but also with additional meta information, like what the data set is actually about, how to connect it with other data sources and these kind of things. And then on the serving side, for a very long time, we've been running with just Presto as a distributed execution engine, which was mostly used for ad hoc querying, but people started using more and more as well for ETL use cases. And at that point, we also hit some limitations where we then said we actually want to do a bigger investment into Spark. And at that point, we also made the decision to evaluate some of the Spark vendors that were out there, and eventually came to the point that we settled on Databricks. And that was the point when we started the journey for our Databricks processing platform, which is what we then have as a centralized point for providing infrastructure to the rest of the company. This also then meant that we started using it more and more often by ourselves. So even though we had these two ingestion pipelines that I was mentioning before already in place with some tools in some shape, we actually started using Databricks here ourselves as well to revamp some of the pipelines and turn them into a state that was much better usable for us. So how does this processing platform now actually look like? The general setup that we have and that we had for a long time is that inside of Zalando, pretty much every team has their own AWS account. This works quite well in terms of like isolating applications and making sure everybody has their own environment, but it also comes with some challenges. And specifically when you want to use a vendor like Databricks and you want to integrate them with your landscape, you have to make sure that you solve some initial setup challenges. The first one was connectivity, because the Databricks control center is always running on the Databricks side, so we need to make sure that they get the proper rights on our side to do stuff like cluster creation and these kind of things, but also that they don't get too many permissions and like direct access to all our data, for instance. What we did on our side then was to actually set up an additional AWS account on our side, which gave the permissions to the Databricks control center to actually create clusters in that and gave them all the permissions that they needed to operate on our side. While at the same time, this was somewhat working in isolation, so they only had the permissions that they actually needed. There were some additional things that we needed to figure out first, like for instance, connectivity issues, like centralized logging, these kind of things that you have that you go through during the initial setup. Now let's have a look at like some of the standard use cases that we are actually covering, and some of them we will actually also talking about later in detail. So let's just say we have Team X that wants to get some data from the data lake, do some computations on that, and then forward it to their own Redshift where they want to use it. What do? They get a Databricks cluster and they do exactly that. Another team wants to act completely independent from the data lake, and this is also to showcase that the processing platform is not just tightly coupled to the data lake. It is directly integrated so that you can use it, but if you just have your own data in your own account and you want to crunch it, you also just get a Databricks cluster and you can do exactly that. And the third use case, and this is one that I already mentioned, is our very own use case that you actually want to connect to the data center and extract some data from there and put it into the data lake for later usage. This is one of the use cases that Stava will cover later as well. So this is like more or less the technical setup that we have, but now I want to take more of a look into how the journey of a team that is starting to use Databricks, how that actually looks like, how they get introduced to the topic and how they start interacting with us from initial introduction up to actually productionizing something. So the very first thing, the introduction to Databricks, the first thing it always goes via us. And there's basically two things that we actively leverage here. One is to actually make use of the resident solution architect that is assigned to us, who is like actively working together with us, who's frequently coming to our offices to also directly sit with our users, understand the use cases, and come up with like initial architectures that you want to go through. Another concept that we developed is that we were using what we call office hours, where we basically, for 2 hours a week, we offer time slots to other teams to interact with us on any given level. At the very beginning, this is a lot about actually the introduction, about like developing the initial architecture, similar things that I mentioned before. But this can go all the way up to actually, I need a developer from that team to solve a very difficult technical problem. The next step is the initial setup. And here we're using an interesting approach, which we call inner sourcing for the configuration of clusters. It's basically like open sourcing, but just inside of Zalando. So what we have is a centralized GitHub repository where we store all the configurations of all the clusters that we are operating. And we even have a template where you can basically fill in all the details about this cluster. This includes which data this cluster is actually allowed to access. This includes which user has access to this cluster, and all kinds of technical details for the cluster itself, which are like what should be the cluster size, instance types, these kind of things. And what we do is we provide this template, and we actually ask the users to fill it themselves. So they actually come to us, they look at that, they actually tailor the things to their needs, and then they do a pull request onto our centralized GitHub repository. And then on our side, we just need to review that, and then we can actually have integrated tooling to then put those things that we were just asking for into production. Next up is the development phase, and this is really where the hard work actually happens in the teams that are using our infrastructure here. Again, like we are heavily interacting here with the teams via office hours, where they can just come to us and like book a time slot and really discuss like deep technical issues. Also, we started having a concept which we call guest developer, where we really allowed to have people directly sit with our team for a week or two and really like directly work inside of the team, work with us together on their problem. And once we brought them up to speed, they can then go back into their team and start educating the other colleagues in their team. And the last step is the productionizing. So here we have full 24/7 support on the infrastructure that we are providing to the teams. So whenever something that is actually running in production that people are actually relying on, whenever there's any problem with these kind of infrastructure, we will always be there to actually support the people, even if like some stuff happens in the night or on the weekend. That's pretty much it from the technical and organizational setup, and now I will hand it over to my colleague Slava to talk about the Databricks use cases that we are running.
Yeah, hi everybody. My name is Slava, and I will walk you through 3 use cases, more on the technical level. So 2 use cases about the way we ingest data from what Max already mentioned from an event bus and from the data warehouse. And then 1 more kind of generalizing use case of how teams are actually consuming this data and how they are self-serving themselves with Databricks. So first, let's start with the data warehouse ingestion. So the problem here was that every team needs data from the data warehouse because this data contains information about sales and other very important information that in e-commerce you can think of. And yeah, basically everybody would like to read this data from the databases. We actually have Oracle and the XSL databases, but you can imagine that if we just give access to everybody, they would just kill the database immediately by overloading it. And another problem is that because historically the data warehouse we have, those databases are in the data center, the connectivity is a problem, and this would just become a infrastructural nightmare to give everybody a connection to their AWS account. So, and let me also mention what are the use cases that teams would like to have. So the standard use cases are historical processing to build machine learning models, to do some historical analytics on data. And the other one is usually reading the newest data all the time and every day. So we had to provide those. And so what we decided to do, this is a very high level picture. Obviously there are many details inside, but I will just give you some glimpse on it. So we decided to use Spark and Spark on Databricks. We created a cluster. We run 1 job per table in the data warehouse. We use Spark JDBC Reader. It actually works pretty well. And we write Delta table. So, and for each table in the data warehouse, there is a corresponding Delta table, which keeps the schema and enforces the schema, which allows us to prevent corruption in terms of evolution of schema that is incompatible. So there are compatible changes like adding new columns, but they're incompatible when the type of the columns, for instance, changes. And this Delta table would save us from those problems. But also, downstream, we have we produce a new snapshot for each table every day, basically merging the previous snapshot with the newest increment of today. And then we write a new snapshot. This was done in this way historically because many teams required data of a table from the data warehouse as of certain date. And we had to write actually new snapshot every day, although it is pretty costly in terms of S3, but that was a requirement that there was no such feature as time travel of Delta, which now exists, which we want actually to look into because this would solve this problem much better. Yeah. Yeah, so, but this works pretty well. So, but let me tell you some of the stories what kind of problems we actually faced while doing this. So problem number one was that JDBC can be simply slow, and when you have one single connection, there can be different circumstances that actually prevent you from having enough throughput so that you can extract and ingest all the data that you need. So like when you have maybe a few hundred gigabytes of data per day, this can become a problem, especially when the data is in data center. What we did, we started to utilize the parallelism of JDBC reader of Spark. And out of the box, you can find the column to use to split your query into concurrent queries so that each query just fetches the range of data by this column. And by this, you can acquire parallelism in reading. And for us, it worked out of the box, increasing the throughput. Another approach is that if the table you have is partitioned, it's actually not another, but just addition. If the table is partitioned, you can create a view on top of this table with a column that contains the ID of the partition. And then this is a different strategy. So you don't have ranges of values, but you actually have only few values. Like for example, if we have a cluster of 4 nodes, each record in this view will have this value according to which partition it belongs. And then you can run your parallelism based on that so that every JDBC connection reads only data with the same partition ID. And this works especially well if the database is partitioned physically. So if it has physical hosts that keep shards of data. So we also have this use case in SSL, for example. Another problem was that the databases are just simply on premises. And of course, connectivity between a cloud and a data center or between different clouds is always a problem. And we had to solve this. But unfortunately, the only approach here is just try to think about this early and try to find the ways how to overcome this in your setup. So we had a special setup when we had a VPN which was shared. And actually, if we had a dedicated VPN just for this pipeline, this probably would work out of the box. But unfortunately, because of historical reasons, because we had this data center for a long time, this VPN connection was shared between many other teams, and we had very unstable connectivity. So actually, what we are doing now, we are trying to get a direct fiber connection to this data center, so that which will be used only by our department probably, so that we can have the very stable, high throughput, and we can extract all the data very easily. Another advice, just try to move your database to the cloud. We are also working on this. This takes always years. So when I joined Zalando, there was a plan it was 2016, there was a plan that 2016 is the last year we're using data centers, so we're still there. Yes, another problem is that you can actually overload your database when you start using parallelism. So what I mentioned in the beginning, if we give access to the database to all the teams, suddenly they just crash it. And the same here, if we ourselves as one team start reading with parallelism, which is too high, we can just do the same and kill the database. So what we decided to do, first of all, to split based on the data source or on a database, create one cluster, one Databricks cluster for each of them. So in our case, we have 4. So we created 4 different clusters to control the load. And how we actually control it, that first of all, you can create a cluster of a certain size, for example, with just 8 total number of cores, and you will not have more than 8 parallel connections to this database. But actually, there is even better way, because very often in this scenario, you are bound only to the network. You're not bound to CPU or memory or disk. So your resources just are wasted very much, and you're paying for nothing. But we found a way to use this environment variable Spark worker cores that allows you to use the smallest instance. For example, we are using R5 large, which just has 2 cores, but we can specify the number of cores the cluster should think it has. And then, for example, we specify 11 for one of the databases. And then we see 11 concurrent tasks of Spark jobs overall, not in one job, but across all the jobs running. And we can control the amount of load we put on the database. Yeah. So then let me move over to the second pipeline, to the event bus. Event bus is a system that allows microservices in transactional world to communicate. So it is not meant to be used for analytical processing. And that's why it only keeps data for 4 days in our setup. but many people, many teams in the company, they actually want to do analytics on the data from the event bus. And both historical analytics and analytics in real time. So we had to solve this problem somehow. So what we did, again, very simplified diagram. But the idea is that we created a cluster, multiple Spark jobs, one per topic in the event bus. So event bus is on top of Kafka, so I will just say topics. And we eventually write, again, as delta tables, every single topic. And here, unlike in the previous use case when we were creating different snapshots every day, here we actually have for each topic one delta table that we continuously update. So we just append data, and any other team can create their structured streaming job, attach to this delta table, and read it as well continuously. And this is the example of continuous applications that actually works very well. Many teams are using that. And they can do continuous processing of data or streaming processing, but they can also just read the data from this delta table for a month or for half a year to do some machine learning model or for some report, like retrospective report. So again, there was many problems that we faced. The problem number one was that every message or every event going through the event bus is just a JSON object. And JSON schema is a very powerful thing that allows you to have much more than schema that you can have in Parquet or in a relational database. So, and what happens actually, if you're familiar with JSON schema, you know such thing called additional properties. And that means that there is in the schema registry, there is schema that is kind of static and specified, but then every single event can have additional fields that are not specified anywhere. And in one event, this field can be, for example, of type string, but in the other one, it can be of type object. And we will just try to ingest this in the delta table. It will obviously fail. So we had to somehow work this around or kind of solve it. And we decided to make the pipeline customizable so that schema is not an inherent part of the pipeline, but it's a pluggable entity so that we can use different schemas at different times, update them, and so on. And we actually ask consumers of those delta tables that know what kind of data goes through the event bus to provide this schema, because they understand that, OK, here, this field I don't need at all, or this field I just want to treat it as a string, no matter if maybe it comes as an object, but I know what to do with this using from JSON function of Spark, for example. And for this, we used inner source. We're actually big fans of inner source. And inner source means that teams simply submit a pull request to our central repository where they specify the schema either as the Scala struct type or is a JSON representation of that. And then we use it and pipeline runs. The problem number two is that we have around 3,000 topics in this event bus. That's a pretty high number. It is actually around 2.5 terabytes of data per day and I think around 200 megabytes of data per second. But even not this is a problem. This you can scale out with scaling the cluster. Actually, the problem happens is on the control plane. If you try to run 3,000 Spark jobs on one cluster, you will kill the driver. You can use the biggest instance for the driver node. You will still, it will start become unavailable, unhealthy, have GCs, and so on. So what we did, we grouped Spark structured streaming jobs into families, and we actually ran so what I mean by family is that we took, for example, 40 jobs. Each of them was a different job run in Databricks. And we just merged them into one Spark job where we have a for each loop. And we just trigger all 40 of them inside of one Spark job. And this solved the problem of the driver just out of the box. Actually, thanks to the Databricks RSAs, they introduced this approach, and they helped us a lot here. So we created one Databricks job per family. This is also much easier to manage because we had those, we tried 80, for example. We now running just 80 out of 3,000, but we are ramping up a lot. And like even running 80 concurrent job runs is not very manageable, or if you have 80 jobs in the Databricks UI, it's also you don't like it. And yeah, we also create a different cluster for each of these jobs. Actually, we're using job clusters here. The transient or ephemeral clusters, which works really well. We don't have actually to care about the cluster on a permanent level. We just create it. It runs whenever we need to do maintenance or something. We don't have to think about what happens to this cluster. all the data is saved in the checkpoint because this is Spark structured streaming job. And of course, we had the problem of small files. So there is a trade-off here that you can have very low latency. Maybe you want to have a latency of 1 minute or a few minutes, but then you will produce very tiny files. And you can have kind of longer latency, maybe 1 hour is okay for you. You can have bigger files, but still you cannot fully control the size. So you can kind of play around with it, but yeah, it's not perfect. So what we did, we simply decided to run optimize every night for every topic we ingest. And this takes quite a lot of time. We had to optimize this optimize to only run it for the newest partitions. And like in this inner source approach, we actually asked teams also to provide how they want to sort, what should be the latest partition, and things like this. So there are quite some more details there. I will not cover them here. But anyways, in the end, we just run optimize, and we don't really care about how to achieve latency and size trade-off. We just decide on the latency we want. We specify trigger an interval of 15 minutes, and then optimize command will do the job. And we use job clusters again for the optimize command. This is okay, again, very nice because you don't have to think about those clusters when they disappear. This happens in the night, and then they just don't exist anymore. So now we have two types of data tables, let's say. One that are getting populated all the time from the event bus, the other ones that are getting created new snapshots every day. How do teams actually use them? So Max already mentioned the setup, how our teams creating clusters and so on, how do they, what do they do? I will just repeat this very quickly. So we have this centralized control plane where we create those clusters, edit them, give access. And then every team can have one or multiple clusters. And actually, we already ramped up like 40, 50 teams and maybe 70, 80 clusters. And we started just in November. The growth is tremendous. And mostly, the use case is always, it repeats the same pattern. Every team reads data from either delta tables from the event bus, for which they usually create structured streaming jobs, sometimes with trigger once, sometimes with continuous running, or they read a snapshot of the data warehouse data. But anyway, so they do some kind of analytics on that, maybe some reporting or with a building model, and then they write to their S3 bucket, or maybe they write to their Redshift or Dynamo. There can be different use cases. 99% of cases, I would say, they write into their own S3 buckets so that they then do some other things. And actually, they often also attach, so they write as delta tables to the S3 bucket, and then they attach another structured streaming to do something else. That's actually pretty impressive what is going on. Problems that we faced here, the problem number one was how do we actually give access to the data lake data, which is in one or maybe two S3 buckets in one account, which belongs to our team, data lake team. How do we give specific access to specific prefixes to all the other teams? We cannot just let them do that on their own, and we cannot update the bucket policy of S3 bucket because it doesn't scale. You reach the limit pretty quickly. And so we decided to just take this in our hands. We, as a central function, create all those roles. We have tooling around this based on what data sets teams want to access. They don't even have to specify what is the path to the data, but they specify only the name. And we actually generate automatically with the tooling, the policy and the role, and we update all of that. So it's actually pretty nice for them. And the only important thing here is that teams have to provide the so-called data access request approved, which means that they actually have to submit a request describing the use case and why they need this data, especially when it's PII data. Yeah, it's quite a long process. Many teams are being pretty sad about that. But whenever they give us the approved request, we then run our tooling and create the role. So another problem we faced was that level of expertise was actually pretty low when we started. Our team was okay expert, but most of others, they just were either data scientists with experience more from mathematics and maybe from pandas and Python, or just people don't have data engineers in their teams, but they need to do analytics. And like we kind of had to solve this problem somehow, although we didn't have so much resources. And thing number one, again, we did inner source here. So Max already mentioned that. To create clusters and to get access to certain data sets, we ask teams to provide only the definition of what they need, and they don't have to think about the infrastructure. We created office hours to consult the teams. This works pretty well. I think all those 40, 50 teams, they're already much higher in their expertise. We started the initiative of a guest developer so that a developer comes to us for a week and just we work on his problem for a week and teach him. Okay, and the last problem, access from the cluster to the team's resources. Of course, they need to write to their S3, they need to write to their Redshift. So for S3 bucket, which is mostly the use case, you need to do two things. You need to create the policy in the role, and this policy is just full access to the S3 bucket, because bucket still has to give access, so cluster still wouldn't get any access. So the second thing is that the team has to actually go and update their S3 bucket policy with the specific access they want to give to their cluster. This works pretty well. So for Redshift, we also had to do the private link to give the connection so that the team can use credentials and actually write to Redshift. Some other teams are using Redshift Spectrum, just writing to S3 and then getting this data to the Redshift. And I think here, I want to hand over back to Max.
To talk about the lessons learned was the last sentence. Yes, so let's wrap it up with what were actually the big learnings that we had throughout this time. The first thing that I want to mention is understand the capabilities of Spark and Databricks early. This is really important when you want to do such a big buy-in into such a technology like we did here. You really have to know what the system is actually capable of, as well as what it is not. And this is like really important that you can really set clearly what's the scope and what are the things that you can actually do with it. One of the things that's pretty important for us here is to involve the solutions architect of Databricks, because they already saw a lot of use cases, not only in different teams, but also in different companies, and they have a lot of knowledge that you can actually learn from. And this is something that we really leverage a lot and actually get some education even for us, which are inside of our company already pretty advanced. You should do proof of concepts for various different approaches. Not always is the first approach that you are choosing, that you have in mind, also working out. You might always run into trouble when you actually run it on like production scale loads. And this is something that you should discover early and make sure that you actually always have a couple of different solutions in mind that you can fall back on. And yeah, learn Spark. Like the last year since we really started buying into this, for us was a big learning experience. The more you learn, the more you actually also learn how much you don't know. And it's like completely open-end. Like you really have to always get deep. Every new use case is some opportunity to learn something else. And you really have to go down, sometimes even down to the single line of code to understand the features that you're now trying to use. And this does not only end on our side, this also then flows over to actually educating the users. This is one point that I will come to in a sec. Delta tables are great. The cool thing about Delta tables is that it just works out of the box, and there are a couple of good features which we are using here as well. First one is like Delta tables combined with structured streaming enable continuous applications. So you actually can pretty much hook different continuous application jobs into each other, where you just have like Delta tables in between of them. And this is amazing to like fan out certain data sets, and this is what we are leveraging a lot. The transactionality of the readers is really important for us as well, because we have a lot of concurrent writing going on while people are accessing the data, and we really need to make sure that this is clean. Yeah, this small little thing that most of you probably also have heard of, GDPR. This is also where Delta really helps a lot to actually do some progress on the side of the right to be forgotten. Automate the management of your infrastructure. This is like really important because this is actually what helps to scale, not on the infrastructure side, but it helps to scale your team. The more stuff you have to do manual, the more you will just drown in operations and maintenance. And this is really what you have to tackle. And this is really where we leverage some of the things that we mentioned before. So the definitions of the clusters as JSON files allows us to then provide some easy tooling on top of that. And that really allows us to automate a lot of the processes for cluster creation, but also for automatically rolling out the updates of clusters whenever something changes. And one thing that Slava also mentioned before is use disposable infrastructure. This really eases the pain when you actually have a continuous application, a structured streaming job that is running, and you need to shut it down for whatever reason, be it maintenance or be it failure recovery, and you don't need to take care of the state of the cluster anymore at this time. Last but not least, externalize the responsibilities. So this inner source approach that we were talking about so much is working out really well for us, not only in terms of the cluster definitions, but also looking back at the event data pipeline to actually provide the schemas, the transformations, and the layout. Educating your users is like the biggest point, I think, because as Slava also already said, at some point we had to discover that the users that just started using Databricks, the level of expertise they had was much lower than what we would have thought in the beginning. And it's really important to teach them, not only in like directly sitting with them and discussing with them, but also providing good onboarding material, like good documentation, and creating training sessions, like basic training sessions on Spark, for instance. And the good thing here is, like, once you have more advanced users, and you will always have more advanced users than others who are just joining the course, you can actually start building a community. You can leverage the people who already have more knowledge than others to like help out and actually discuss problems with them so that they will not run into the same issues that they did in the past. This is pretty much what wraps it up today. This is what we are having here, what we are using to maintain and operate our processing platform, and how we run continuous applications at the scale of 100 teams with Databricks Delta and structured streaming. I want to thank you for having us here, and if there's any more questions, we might have a bit of time to answer them.
Thank you, Max and Val. We've got 3 minutes. Those were actually quite insightful nuggets of their journey of how they actually picked up Databricks Delta and how they have scaled it, and here to share with you. So we got Mike over here. Can you please line up and ask your question? Yeah, it's on.
Thanks for the insightful session. Can you please elaborate a bit more on inner source, what you really mean by that?
So the concept which we took from the open source part is that you have a centralized GitHub repository where you keep all the configurations and they are just available for everyone, but the contributions come from the outside. So the teams themselves, they prepare what they actually want to have by using a template, and then they open a pull request with us. We are the ones who review that thing, and then it gets just merged, and we have some processes in the back to bring that to production.
It sounded more like different teams contributing to other teams. The guest developer concept that you spoke of,
yeah,
that also you brought under inner sourcing. So was just confused a bit.
So like they are mostly contributing to themselves, basically, because they are providing the definitions that they need for their own clusters. Okay. But the contribution comes from the part that like decentralized entities are basically writing something that then gets merged into a centralized entity. That's where we draw the comparison to open source as well.
Sure, thank you.
Hi, my name is Siva. So you are using parallelized JDBCs, right?
Yeah.
Parallelized JDBCs.
Yes.
So to do a parallelized JDBC connection, we have to find a numeric column and then find out the min and max, right? So what are you doing for the tables which doesn't have numerical columns or which have numerical columns with nulls and empty values?
Yeah, so this is sometimes a problem. But actually, most of the tables we have, they have so many different columns that usually we find something. And as I mentioned, you can also create an artificial view and like provide some sort of artificial column for this. Quite often we have just a parallelism of one. It works as well. So you have to work on like table by table basis and figure out this. Yeah.
Can we use timestamp?
Yes.
Can we use a view which converts the timestamp into a number and use that?
Actually, you can use timestamp.
Yeah.
You can use date, number, and timestamp, I think.
Mm-hmm. And did you see using like CDC logs to actually get the data from data warehouse? Because JDBC is an expensive operation for the data warehouse, right?
No, we don't really do that. We use so it is kind of like this, but a bit manual. So we use a special column which just has last modified timestamp. So this is like CDC implemented by us. Yeah.
I mean, it's a lot of load for the data warehouse, right? If we use multiple connections to load the data. Instead, if we use the logs of the data warehouse, it is like, it doesn't have any load on the SQL data warehouse kind of.
It's a good point. We can try it.
There's a concept called polybase in SQL data warehouse, through which actually you can load the data directly to the HDFS or S3 or any other kind of solution without hitting actually the queries kind of thing.
Yeah, interesting point. Thanks for the advice.
Thank you.
All right, thank you. Give a hand to Max and Viachesl for sharing that knowledge with us. Thank you, guys.